Let me welcome you to this lecture. We have now seen what is the reducible representation of a group as well as what is irreducible representation of a group. We have also seen how one can do block factoring of the matrices for different symmetry operation in a reducible representation and then obtain the irreducible representations. But this block factoring of the matrices for a different symmetry operation in a reducible representation cannot be done randomly because irreducible representation or all irreducible representation of a group follows certain rules, and these rules are obtained from a theorem which is called great orthogonality theorem. Now during this lecture we will learn few uh, important relations that we can obtain from the great orthogonality theorems, and these important relations between irreducible representation will essentially allow us to find out the irreducible representation of a group. So let us learn these important rules or important theorems that one can obtain from the great orthogonality theorem. There are 5 such rules and we will learn these 5 rules now. So the first rule essentially tells us that the sum of square of the dimension of the irreducible representations in a group is equal to the order of the group. We will see what does this mean. So we take the dimension of the irreducible representations that are present within a group. So what are dimensions of irreducible representation? It is nothing but the order of the matrices for different symmetry operations in that irreducible representation. So we take the dimension of the matrices for different symmetry operations essentially, and that is the dimension of the irreducible representation. Now we also know that within a given irreducible representation, the order of all the matrices for different symmetry operations are going to be essentially same, and that is why we will have only one dimension of the irreducible representation, or the dimension of the matrices for different symmetry operations within that irreducible representation are anyway going to be same. So we will use the symbol Li to represent the dimension of an irreducible representation, or L to represent the dimension of a irreducible representation. Now, what is order of a group? We have already learned that is the number of symmetry operations within a group is known as the order of the group, and we usually use the symbol small h to denote the order of a group. So, what does this expression tell us then? That the sum of the square of the dimension of all the irreducible representation is equal to the order h. So if we have total I irreducible representation within a given group, then what we can write the dimension of all the irreducible representation. So let's assume that the dimension of the first irreducible representation is L1. So we take the square of the dimension, that is L1 square. For the second irreducible representation, we assume the dimension to be equal to L2, and so on. We do L3 square, and if we go on till Li square, if we have total I irreducible representation in the group, then if we take the square of these dimensions and then sum it up, we get answer equal to the order of the group, that is the number of symmetry operations within that group. So this is the first rule concerning the irreducible representations. So the second rule states that the sum of the square of the characters of matrices representing different symmetry operations within an irreducible representation is equal to, again, H, that is the order of the group. So what does this say? We take the character of matrices representing different symmetry operations within a particular irreducible representation, and if we take the square of these characters, then the sum of these square of the characters is going to be equal to the order of the group. So we denote this, say, as chi to represent character, and this R is for a particular symmetry operation. So for the symmetry operation R, the character of the matrix representing the symmetry operation R, if we take, and then if we take the square of these, and then if we do sum for all the characters for different symmetry operations, okay, the matrices for different symmetry operations, and then this sum is going to be equal to H. Okay. So this is what is the second rule that we get from, again, great orthogonality theorem, and this is going to be very helpful to derive different irreducible representation in a particular group. So the third rule tells us that the vectors whose components are characters of matrices representing a symmetry operation in two different irreducible representations. Are orthogonal to each other. So these characters of the matrices representing different symmetry operation within a irreducible representation are components of actually vectors, or one can express vectors by using the characters of the matrices representing different symmetry operations within a given irreducible representation. Now if we take the different vectors that we get by or whose components that we get from the characters of the matrices representing different symmetry operation, then these vectors are going to be orthogonal to each other. So what does this mathematically? How do we express this? So if we take again sum over chi for the irreducible representation, say gamma I and gamma j, we have character for symmetry operation R for the gamma I irreducible representation is equal to gamma chi I R. So if we multiply this with ijr, then the sum over for all symmetry operations, if we do this exercise, then we will get answer equal to 0 because the vectors whose components are characters of matrices representing a particular symmetry operation in two different two different irreducible representations are essentially orthogonal to each other. The third and this is the third law or rule that we should know regarding the irreducible representation, and the fourth rule tells us that the characters, or we should write that within a given reducible or irreducible. So this particular rule is true for reducible representation as well as for irreducible representation. So within a given reducible or irreducible representation, the character of matrices representing symmetry operations within the same class are equal. So what does this tell us? That if we take the symmetry operations within the same class, because we know how to find out class by doing similarity transformation, and we know the constituents or different symmetry operations within a given class. So if we take the matrix representation for different symmetry operations within the same class, and we look at the characters of these matrix representation, both for reducible representation as well as for irreducible representation, what we will see that the characters of the matrices for different symmetry operation within the same class are essentially equal. So if you have noticed carefully, you would have seen in the last lecture we have derived or we have written the matrix representation for different symmetry operations in C3 point group, and we have also obtained the irreducible representations, two irreducible representations for the C3 point group by doing block factoring of the three-dimensional matrices within. And there, if you have noticed carefully, you would have seen that the character of the matrices representing C3(1) as well as C3(2) operation are essentially same for both reducible representation as well as for irreducible representation. Similarly, sigma v dash, sigma v double dash as well as sigma v triple dash, they are all in the same class in the C3 point group. And again, if you notice carefully, you will see that the characters of the matrices for sigma v dash, sigma v double dash and sigma v triple dash are again same for in case of the reducible representation we have written as well as for the two irreducible representation that we have written for these symmetry operations. Anyway, so this is the fourth law regarding reducible as well as irreducible representation, and this is very helpful in finding out the irreducible representation of a group. So the fifth and the last law that we should know is that the number of irreducible representation within a group is equal to the number of classes in the group. So we have already learned that there is a finite number of irreducible representation within a given group, and now we know how many irreducible representations are going to be present within a group just by finding out the number of classes within the group. So because the number of irreducible representation is simply equal to the number of classes that are present within the group. So this will help us in finding out the irreducible representation again. So these are the 5 rules that we need or that we obtain from the great orthogonality theorem, and these 5 rules allow us to derive different irreducible representation within a given group. So let us do that exercise for the C2V point group. Let us try to find out the irreducible representations present in the C2V point group. So we know in the C2V point group there are 4 symmetry operations. So the order of the group or H is equal to 4 for the C2V point group. Secondly, we have also found out that the number of classes in the C2V point group is equal to 4, as all the symmetry operations in the C2V point group constitute their own classes. So that from the 5th rule we can now easily tell that since there are 4 classes in the C2V point group, there must be 4 irreducible representation in the C2V point group. So we know the number of irreducible representation in the C2V point group. Let's write or let's denote these irreducible representations as gamma 1, gamma 2, gamma 3 and as gamma 4. Since we know that there are only 4 irreducible representation in the C2V point group. So then let's find out the characters of the matrices for different irreducible representation in the C2V point group. So what we will do first is we will use the first rule that we have regarding the irreducible representation that we have learned, which tells that the square of the dimension of the matrix representation for different symmetry operations within different square of the dimension of the irreducible representations within a given group is equal to the order of the group. Since we here there are 4 irreducible representations, let's assume that the dimension of the first irreducible representation is L1. So we take L1 square, and the dimension of the second irreducible representation gamma 2 is equal to L2. So L2 square and L3 square, let's take the dimension of gamma 3 to be equal to L3, while the dimension of gamma 4 is equal to L4, and we take the square of these dimensions and then sum them up, and the answer must be equal to H, and we know that the order of the group here is equal to 4. So this expression L1 square plus L2 square plus L3 square plus L4 square is going to be equal to 4. This is what we know from here. So this expression, as we should note that the dimension of a irreducible representation, or even for reducible representation, or the order of the matrix representations within the irreducible matrix representation for different symmetry operations within the irreducible representation has to be a positive integer, as the order of the matrix cannot be equal to 0, neither it can be a negative number. Order must be positive integers, and that is why the values L1, L2, L3 or L4 must be positive integers here. And the only possible solution for positive integers, if we assume that L1, L2, L3 and L4 are positive integers, then the only possible solution that we get by assuming that all L1, L2, L3 and L4 are equal to +1, because then only we can get answer equal to 4. So L1, L2, this essentially tells us that L1, L2, L3 and L4 are all equal to +1 here. Or what it means that all the 4 irreducible representations in this C2V point group are one-dimensional irreducible representation, or the matrix representation for different symmetry operations within all the 4 irreducible representations in the C to B point group are these matrices are of order 1 and only one row and one column are present in these matrices. So since we now know the order of the or the dimension of the all the irreducible representation in the C to B point group, they are all one-dimensional irreducible representation. We also know at the same time the character of the identity operation because for all these representations, because the character of the identity operation is essentially equal to the dimension of the irreducible representation. As for one-dimensional irreducible representation, the matrix representing the identity operation is going to be a unit matrix of order 1, for which the character is going to be equal to 1. So the character of the identity operation for within a given irreducible representation is essentially going to be equal to the dimension of the irreducible representation, and that is why we know the character of the identity operation in case of all these one-dimensional irreducible representation is essentially going to be equal to 1. So we know that the character of the identity operation for all the irreducible representation, and we need to find out now the character of the matrix representation for other symmetric operations in all of these irreducible representation. And in this, the second law will help us. That the second law tells that if we do chi I r whole square and then sum it up for all the symmetric operations for a given irreducible representation, then we get answer equal to h. So let us do this exercise for the first irreducible representation. That is, let's do chi 1 r square is equal to h. We can write. So if we do this for chi 1 for the first irreducible representation, if we do, that is, we have to do sum over of chi 1 e for the identity operation, the character of the matrix representation for identity operation, and we take the square of that. Then again for chi 1 only, for gamma 1 only, the character of the C2 operation we take, and then do square. Then we do chi 1 sigma v xz as well as chi 1 sigma v yz, and again do square, and then we get answer is equal to h. Again, h is equal to 4 here, we know that, and this is what we will get. Now we know the value of the matrix representation or the character for the matrix representation for identity operation in case of the first irreducible representation, that is equal to +1. So we can write +1 square, and then the rest here will follow, and this will be equal to again 4. Now we know that the value of chi for these symmetry operations in case of the first irreducible representation, only one value will satisfy this expression for two values, not only one, that is chi I r. If we write plus minus equal to chi 1 r for all the symmetry operations, we can write equal to plus minus 1, and then this expression is going to be satisfied, this particular expression that we have written over here. So let us now put character for all symmetry operations for the first irreducible representation equal to +1 here, because in case of all the point groups we will have an irreducible representation for which all the characters are going to be +1. We call this the symmetric irreducible representation, or this is the most symmetric irreducible representation, and for this particular irreducible representation all the characters for different symmetry operations are going to be equal to always 1. So this particular irreducible representation is present for all the groups here. So now we know the characters of the first irreducible representation, and we will now have to write the characters for the second irreducible representation. Again, we have the choice to write these characters as either equal to +1 or as -1. We cannot write all equal to +1, because in that case the third law which tells that the vectors whose components are essentially characters for different symmetry operations within in two different irreducible representation have to be orthogonal to each other, and this will violate the orthogonality rule if we write all the characters here equal to +1. So two of the characters are going to be -1 and two are going to be +1. Then in that case it will follow the orthogonality rule. We will see how. So let's write this as +1 and these two as -1, and then now let us see if gamma 1 and gamma 2 or vectors whose components can be expressed by characters of different symmetry operations in two different irreducible representation are orthogonal or not. These gamma 1 and gamma 2 follow the orthogonality rule or not. Let us find it out. So if we do so, what we will do is that we will take chi1 r and chi2, that is gamma for gamma 2, the characters will express as chi2, so this must be equal to 0. So let's find out this particular expression for gamma 1 and gamma 2. So if we do, so that is chi1 r, so chi1 e, chi2 e, we will write plus chi1 c2, chi2 c2 plus chi1 sigma v xz, chi2 sigma v xz plus chi1 sigma v yz, chi2 sigma v yz. So this is what this must be equal to 0. Let us find whether it is equal to 0 or not for this to be for these two irreducible representation to be orthogonal to each other. So if we do this exercise, what we will find, chi1 e is equal to 1, chi2 e is equal to 1 again. So 1 into 1 plus chi1 c2 is equal to 1, and chi2 c2 is also equal to 1 plus, so chi1 sigma v xz is +1 and chi2 sigma v xz is equal to -1, and that is the same for sigma v yz as well. So what we get, 1 here, 1 from here, and this is going to be -1, and this is also going to be equal to -1. So answer we will get equal to 0. So this essentially tells us that these two irreducible representations that we have already we have seen or we have written over here, they do follow the orthogonality rule, and the characters that we have written for the second irreducible representation is correct because it follows not only the second rule, which tells that the sum of the square of the characters is equal to the order of the group, also it follows the third rule, which tells that the vectors whose components are essentially characters of symmetry operations into irreducible representation are orthogonal. So these values or these characters essentially follow both of these two rules, and they must be correct. So from here, what we know, again, we can easily write the characters for different symmetry operations in case of gamma 3 and gamma 4 as well, because now we know in order to be orthogonal, the characters must be, two of the characters must be +1 and two of the characters must be -1, and we can just simply juggle this up to write the characters. So let's write -1 here and -1 here and +1 and -1 +1 -1. This is going to be another combination of characters for this, and that will be for gamma 4. So these are the characters of the irreducible representations in case of the C2V point group that we have found out by following these 4 rules. So next what we will do the same exercise for the C3V point group, and we'll see if we can find out the characters of different irreducible representation of the C3V point group. So let us quickly recollect that in case of the C3V point group, there are 6 symmetry operations. That is identity operation, C31, C32, sigma v dash, sigma v double dash, and sigma v triple dash. Now we have, in case of the C3V point group, there are 6, so H is equal to 6 in this case, and we know that there are 3 classes in case of the C3V point group, that is E forms a class, this C3(1) and C3(2) forms a class, again sigma V dash, sigma V double dash and sigma V triple dash forms another class. So there are total 3 classes in the C3V point group, and we can write easily then that there are going to be 3 irreducible representation in case of the C3V point group, because the number of irreducible representation is equal to the number of classes, and that is why we have 3 irreducible representation here. So now if we assume the dimension of these irreducible representation to be L1 and L2 and L3, then L1 square plus L2 square plus L3 square must be equal to the order of the group, that is, it must be equal to 6 here. So in this case, if we assume again, since we know that L1, L2 and L3 are all positive integers, so only one combination or one solution is available to us for this to be equal to 6, that is L1 to be equal to 1, L2 to be equal to 1 and L3 to be equal to 2. If we do, then only these combinations, or L1, L2, L3 when we do the square and then sum them up, will be equal to 6, because here we will get 1 plus 1 plus 4, that will be equal to 6. So what it tells us that in case of this C3V point group, there are 3 irreducible representation, and we know the dimension of these 3 irreducible representation. Now there are 2 one-dimensional irreducible representation, and there is 1 two-dimensional irreducible representation in case of the C3V point group. So we can also write the character of the identity operation in case of these 3 irreducible representation now, because the character of the identity operation we have seen is essentially equal to the dimension of the irreducible representation, and these are going to be 1, 1, and 2. So just by looking at the character of the irreducible representation, we can easily tell also the dimension of that particular irreducible. Now the character of the identity operation in a irreducible representation, if we look at, then we can tell the dimension of the irreducible representation, the other way around. So now we also know from the fourth rule that says that the character of symmetry operations within the same class are essentially same. So essentially what we can write that this chi1 C3(1) and chi1 C3(2), they must be equal. Similarly, chi1 sigma v dash, chi1 sigma v double dash and chi1 sigma v triple dash are also equal. So we will be writing the same character 2 times here, same number 2 times here, because these 2 numbers are essentially going to be same. That is why instead of writing these numbers 2 times, we write it just once, and we just write that there are 2 C3 operations, and these C3 operations will have the same character over here, because we know within this class, within the C3 class, there are 2 symmetry operations. So that is why we write 2 C3, and we can write the character in the same place for both of these 2 symmetry operations. At the same time, for all of these 3 symmetry operations, sigma v dash, sigma v double dash, and sigma v triple dash as well, instead of writing them 3 times, we can simply write them as 3 sigma v. That will tell us that there are 3 symmetry operations within this particular class, and their characters we can write at one place over here, because all of them are going to be essentially same. So this will make our table a little bit short, or it will be easy for us to write as well. So let us now find out the characters of the symmetry operations for here. So we have already said that there is going to be one totally symmetric irreducible representation for which the characters are going to be equal to +1 and +1. So let us see if it satisfies the second law, which tells us that the sum of the square of the characters for different symmetry operations within an irreducible representation must be equal to the order of the group. So if we do so, 1 is the character for the identity operation. Again, there are 2 C3 operations, C3(1) and C3(2). For both of them, the character is equal to 1. So we write this one for the C3(1) operation, and this for the C3(2) symmetry operation. And instead of writing them 2 times again, what we can do is that we can write them to be equal to 2 into 1 square, because we'll have essentially be writing 2 times 1 square to write the characters for C31 and C32. So instead of that, we just write 2 into 1 square over here and 3 into 1 square, that is the character for the sigma b or symmetry operations or the here. So this is going to be equal to 1 plus 2 plus 3, and this is equal to 6. So these combination of characters do satisfy the second law for irreducible representation. So now let us find out what combination of characters will satisfy for the third or for the second irreducible representation. Again, in this case, this is also one-dimensional irreducible representation. So again, for this also we can write these numbers to be either equal to +1 or -1, and that will follow the second law essentially. That will, if we write -1 over here, if we write -1 over here and +1 over here, that will satisfy the second law as well as the third law, because then we can write 1 square, then 2 into 1 square, and 3 into -1 square. This will again be equal to 6. But this combination is going to satisfy the third law as well, that is the orthogonality law, which you can find out quickly over here again. That there is 1 into 1 for the character of the gamma 1, and identity operation for gamma 1, and identity character of the identity operation for the gamma 2, plus 2 into +1 again here into +1 plus 3 into 1 into -1. If you see, this is +1 +2 -3 equal to 0. So these combination of characters only satisfy the orthogonality rule. If you write -1 over here and +1 over here, that will not satisfy the orthogonality rule, even though it satisfies the second rule for the sum of the square of the characters to be equal to the order of the group. So if we write -1 here, +1 here, that will not satisfy the orthogonality rule, and only these combination, that is +1 +1 -1, will satisfy the orthogonality rule. So this is how we can find out the characters for the second irreducible representation. Now we need to find out the characters for the third irreducible representation, which is a two-dimensional representation. Now again, what we have here, if we go for the second rule, it says the sum of the square of the characters, that is 2 square plus, so let's assume this to be chi3 c3 and chi3 sigma v, these two characters as. So then chi3 c3 square plus chi3 sigma v square. So this is must be equal to 6. That is the order of the group. So essentially what we can write from here, chi3 c3 whole square plus chi3 sigma v square is equal to 2. So let's assume this to be expression number 1 for us. And now we will use the orthogonality theorem and then write two more expressions. That is, if we use the orthogonality rule for gamma 1 and gamma 3, we can write that that is going to be equal to 1 into 2 plus 2 into 1 into chi3 c3 plus 3 into 1 into chi3 sigma v is equal to 0. So let's try to simplify this. So 2 plus 2 chi3 c3 plus 3 chi3 sigma v is equal to 0. That we obtain this expression we obtain by using the orthogonality rule for gamma 1 and gamma 3, and let's call this expression to be equal to this expression 2. So if we again use the orthogonality rule for gamma 2 and gamma 3, then we will get another expression, that is 2 plus 2 chi3 c3 minus 3 chi3 sigma v equal to 0. that is going to be expression 3. Here it is going to be minus 3 chi 3 c sigma v, because minus 1, 3 into minus 1 chi 3 sigma v. So that is why this is going to be minus 3 chi 3 sigma v. So now let us do 2 plus 3. Let's add these two expressions, the expression 2 and the expression 3 to find out, to solve, to find out the unknown variables over here, unknowns, the chi 3 c3 and chi 3 sigma v. So if we do so, then here it is going to become plus 4. This is 4 chi 3 c3, and these two are going to get cancelled. That is 3 chi 3 sigma v minus 3 chi 3 sigma v. So that will not be there in the final expression that we get, and we add up these two, equation 2 and equation 3. So this is what we will get. So this will give us chi 3 c3 equal to minus 1 essentially. And when we place the value of this, or we substitute the value of chi 3 c3 in any one of these two expressions, or say in this expression over here, what we will get that chi 3 sigma v is equal to 0. So we can easily find out the value of chi 3 c3. This is equal to minus 1 we obtain, and chi 3 sigma v has to be equal to 0. And this combination of characters for different symmetry operations in case of the third irreducible representation now satisfies not only the second law, which is as well as the third law, that is the orthogonality law, and we have obtained these combinations by just using the orthogonality rule. So this combination of characters are going to follow the orthogonality law again. So this is how one can find out the irreducible representations or the characters for different symmetry operations in all the irreducible representation within a given group. So you will again have to do this exercise for different point groups. That is, you have to use these 5 rules and then find out the characters for different symmetry operations in case of all the irreducible representation. So this essentially brings us to the end of this lecture. What we have learned during this lecture are 5 important rules that we obtain from the great orthogonality theorem, and these rules or relations between irreducible representations essentially allow us to derive all the characters of different symmetry operations for the irreducible representation. So we will now be able to build the character, something known as character table for different point groups by using, or we will be able to write the characters for different irreducible representations by using this particular all these 5 rules. So we should do this exercise for different point groups, and you will have to do this, of course. And with this, let me conclude this lecture. I thank you very much for being with me during this lecture.